Hey, Big, who's the smartest person who ever lived?
Probably Einstein.
Yep, that's right. And Einstein once submitted a paper to a scientific journal saying that gravitational waves didn't exist. A reviewer sent it back and said, "You made a math error."
Wait, Einstein got fact-checked?
And the reviewer was right. It took 100 years to prove it. Let's go find out why. I'm Erica, and this is my son, Big. Our brains work best when we're moving, when we can touch things, and when we can ask questions the second we think of them. Traditional classrooms weren't really built for us, so we're homeschooling, learning our way through America's wildest and most interesting places. Today, we're driving through the desert of eastern Washington to visit one of the most extraordinary scientific instruments ever built. By the end, you'll understand how scientists detected a signal that had been traveling through space for 1.3 billion years.
And I'll warn you, I had a lot of questions.
Okay, let's go.
Why are we in the middle of the desert? There's literally nothing here. What are those really long tube thingies? They go so far.
Every question you asked, we're going to answer before we pull into that parking lot. And by the time we do, you'll understand something that took the smartest people on Earth 100 years to figure out. Before we go in, you did some research. What does LIGO actually stand for?
Laser Interferometer Gravitational Wave Observatory.
Which sounds pretty complicated, right? Let's break it down so it makes sense for our listeners. All right, first word is
Laser
they're using lasers. What's the second word?
Interferometer.
Yeah, that means it's a device that uses the way light waves interfere to measure teeny tiny distances.
Teensy.
Yes. What's the third word?
Gravitational wave.
Yes, that's what they're hunting for. And the last word?
Observatory.
Yeah, that just means it watches the sky. But instead of light, it watches for ripples in space-time itself. So LIGO is basically a giant ear made of lasers that listens for the universe shaking.
Kind of. The scientist was specific about this. It's not actually sound. Sound is pressure waves in air. This is the geometry of space itself oscillating.
Right, which is cooler. And it's not just here. There's 2 sites in the United States, right?
Right. This one is in Hanford, Washington. And there's one in Livingston, Louisiana. They need 2 because if one detector picks something up, it might just be a truck or an earthquake. But if both catch the same signal, that's when you know it's real.
Look at those arms. They go in an L shape, 2.5 miles in each direction. The engineers actually had to account for the curve of the Earth when they built it. The ground at the far end of each tube had to be raised up because the laser inside has to travel in a precisely straight line, over 4 kilometers. And the Earth actually curves away by almost a meter.
They built the ground up because of the curve of the Earth?
That's right. Now, this is the quietest scientific instrument on Earth. The thing that this place is trying to detect is so faint that even a truck on a highway 5 miles away is louder. Ocean waves on the Oregon coast are louder. Your heartbeat standing right next to one of those mirrors would be louder.
My heartbeat would wreck the experiment?
Your heartbeat is too loud for the most sensitive machine ever built, which honestly, I think is kind of fascinating. That's why it's here, in the most boring, flat, quiet, remote stretch of land. And here's one more thing. Before the LIGO existed, this land was part of the Hanford site. They used to make plutonium for nuclear weapons during World War II. Same emptiness, completely different purpose.
The scientist mentioned LIGO is in a clean corner of the reservation, nowhere near the waste storage area, which, good to know.
Good to know. Let's go inside. Okay, so we got incredibly lucky today. Once a month, LIGO opens for a tour led by an actual working scientist, someone who uses this instrument for their research. And that's exactly what we got.
I'm Rahul Kumar, and I'm working as a detector engineer over here. I'm also a staff at California Institute of Technology. LIGO is jointly run by Caltech and MIT. So, first time at LIGO, or have been here before?
The first time for us. Gotta read this big and strong. She has a question.
Did you find a black hole?
Yes, we found several black holes. Black hole is an extremely dense object. It's basically a dead star. But black hole in itself can't produce gravitational wave, which can be detectable on Earth. You need a pair of black holes which is spinning around each other, and then they collide. And the collision will produce so much amount of energy that is just vibrate the entire universe.
The control room isn't what you'd expect. It's not dramatic like all of the scientists in those space movies. It's a quiet room full of monitors showing data streams, and there are just usually like a handful of people sitting at computers. It's almost boring until you understand what those screens are showing.
The scientist explains that what you're looking at on those monitors is the detector's sensitivity in real time. It's like a health readout for the machine. And when a gravitational wave passes through, you'd see a signature appear in the data. It's like a specific shape. It's usually like a mountain, then down.
And do you want to hear what it sounds like?
Whoop.
Yes, that's great. Now let's listen to the actual scientific version. So, if it's a real signal, what you'd hear is this specific chirp pattern at both sites, just milliseconds apart.
So what you see is you have this central loop over here, and then you have the two arms, which is 4 kilometers long.
And what's actually happening inside those arms is this: a laser beam enters the detector and hits a beam splitter, a mirror that sends half the light down each arm.
Wow.
Each arm is 4 kilometers long, and inside is essentially a vacuum, one of the largest vacuum systems on Earth, because even air molecules would interfere with the measurement. And then at the end of each arm is a mirror. The laser bounces back and forth between mirrors hundreds of times before returning, which effectively turns 4 kilometers into over 1,000 kilometers of total distance traveled. That is how you get the sensitivity.
And normally, when the two beams come back and recombine, they cancel each other out perfectly. No light gets through.
But if a gravitational wave passes through and changes the length of one arm, even by an almost impossibly tiny amount, the beams come back slightly out of sync.
A flicker of light gets through, and that flicker is the signal.
By how much do the arms change?
1/10,000th the width of a single proton.
What? A proton is already too small to see. That's 1/10,000th of that?
Yeah.
So this is our control room. Every terminal is taken up by someone who's working on different aspects of it, is interferometers. And then you see a lot of monitors over here. Each monitor is tracking different subsystems, the health of a subsystem, and then how we are working.
Standing in the control room, knowing what those screens are watching for, changes how you think about the universe.
Like the universe is always talking. We're just finally learning to listen.
Exactly. And this machine is basically always running, always listening. After the control room, we went through the children's exhibits. And even as the adult in the room, these made things click in a way the control room screens couldn't quite do on their own. First, the vortex. Drop a marble in and watch it spiral down to the bottom.
It curves inward. It's not going straight. It's following the shape of the funnel. And that's gravity. Massive objects curve space, and other things follow that curve.
That's such a good explanation. You did such a great job. Then there's the pendulum wave machine. This long row of rods, each one weighted at both ends, all connected along a central spine.
It's so cool.
When you push one end,
the motion travels all the way down, but each individual rod just pivots in place. It doesn't go anywhere.
And that's what gravitational waves do. The wave travels through space while space itself just wiggles as it passes.
But the scientist was specific about this too.
Now, suppose if there is a gravitational wave which makes one arm longer and the other arm shorter.
It's not exactly that the mirrors get nudged. It's the space between the mirrors that's stretching and squeezing. The mirrors are just along for the ride.
So LIGO isn't measuring the mirrors moving.
It's measuring space moving.
All of these exhibits are showing you the same idea from different angles. Space isn't an empty container, it's a medium. And just like any medium, it can carry waves.
And LIGO is how we hear them.
Here's the history that makes everything we saw even more extraordinary. Albert Einstein published his theory of general relativity in 1916. Buried in the math was a prediction. Massive accelerating objects should send out ripples in spacetime, gravitational waves. So when two black holes collide in the universe, there's a huge explosion, and that very explosion will ripple spacetime. But when he calculated how small those ripples would be by the time they reached Earth, he concluded it would be impossible to detect them. Don't even bother looking, he said. Then, in 1936, when he went back and tried to prove they didn't exist at all, he submitted a paper to a journal, which brings us back to where we started.
The journal sent it to an anonymous reviewer.
This is typical for science, just so you know. They send papers out to other scientists who give peer review and feedback. It's kind of like when your teacher corrects your paper.
And that reviewer found a math error.
Einstein was furious. He pulled the paper and sent it elsewhere. But his assistant talked to the reviewer, came back and said, there actually is a mistake. So he made a mistake with his math. Einstein eventually admitted it. The paper came out with the opposite conclusion. But for decades after that, most physicists still agreed that detection was hopeless. The waves were probably real, but they were so small that finding them was probably impossible. Then a physicist at MIT named Rainer Weiss spent years working through exactly how you'd build a machine to do it. Every obstacle, every noise source. By 1972, he had the whole blueprint published. Construction started here in 1994. I was 8 years old at that time, just as old as you are. The detector began taking data in 2001.
And it found
Nothing for years. So between 2010 and 2015, they shut the whole thing down, pulled it apart, and rebuilt it 10 times more sensitive. Advanced LIGO. And on September 14th, 2015, during final testing, not even officially in science mode yet, the signal arrived. A computer caught it first. Scientists woke up to alerts on their phone, and immediately everyone was suspicious because the signal was too perfect. And LIGO had spent years secretly injecting fake signals into its own system as practice drills. Nobody knew when they were coming.
they were trying to trick themselves?
Yeah. And for weeks, they checked everything: trucks, earthquakes, equipment glitches. Staff at both sites in Washington and Louisiana were asked where they were at 5:51 a.m. The signal had arrived in Louisiana 7 milliseconds before it arrived here, consistent with the speed of light between the two sites. The shape matched Einstein's equations exactly.
It was real?
It was real. On February 11th, 2016, the director walked to a microphone in Washington, D.C. and said this.
Ladies and gentlemen, we have detected gravitational waves. We did it.
From Einstein's pencil and paper in 1916 to this desert in 2015, a century of people saying it couldn't be done.
Did Einstein know?
No, he died in 1955. He never even knew.
That's really sad.
Maybe. Or maybe being proven right 60 years after you're gone is kind of its own win.
Einstein was right.
Einstein was finally proven right.
Is it still listening right now?
Yes, hundreds of detections since 2015. It's detected black holes. It's also detected neutron stars, which are the incredibly dense collapsed cores of dead stars. And when two neutron stars collide, the explosion forges heavy elements, including gold. Scientists believe that neutron star collisions are actually responsible for most of all of the gold in the universe.
So my sister's earrings are from space?
They might be from space.
She's never gonna let that go.
The scientist talked about where all this is heading. Do you remember what he told you?
So LIGO can only hear certain frequencies. The quick chirps of the black holes are the ones we talked about. But the lower frequency waves are drowned out by Earth itself vibrating. To hear those, you have to go to space.
Yes, and that's LISA, the new project they're working on. LISA stands for the Laser Interferometer Space Antenna. 3 spacecraft flying in a triangle, laser beams connecting them across 2.5 million kilometers. It's planned for launch by the European Space Agency in 2035. It could hear supermassive black holes emerging and maybe the echo of the Big Bang itself.
Wow!
Ah,
We're gonna have a Big Bang? But it's already over.
the gravitational waves that have been traveling since the very first second the universe existed.
Since before everything.
Yep. And back here on Earth, the ground network is expanding too. Kagra in Japan is already running. It's underground, built in a mine, and uses sapphire mirrors cooled to near absolute zero to reduce vibration.
Underground?
Yep. Virgo is in Italy, and LIGO India just broke ground in 2026. And when that comes online around 2030, 5 detectors spread across the planet means you can actually pinpoint where in the sky a signal is coming from.
The scientists said it's like going from hearing a sound to being able to turn your head and find out where it came from.
All right, here's my one thing. Einstein asked a question in 1916 that nobody could answer for 100 years. Rainer Weiss asked a question that most people said was pointless and spent decades proving them wrong. The scientists building LISA are asking questions right now that we don't even have the tools to answer yet. So they're building those tools. Every discovery we talked about today started with someone asking a question that seemed too big, too hard, or too weird.
Or impossible.
Exactly. And the universe, it's not done surprising us. It's barely even started. The next question hasn't been asked yet. And maybe you are the one who asks it.
I have like 50 more questions.
Well, then let's go find a scientist. All right. So, the LIGO Hanford Observatory sits on the ancestral lands of the Wanapum and Yakima peoples, who have been stewards of the Columbia Basin since time immemorial. Their connection to this land continues today. The Exploration Center at LIGO Hanford is open to the public and free of charge. Once a month, visitors can join a tour led by an actual LIGO scientist. Visit roamschoolfamily.com for activity guides, questions to ask on your LIGO tour, and links to LIGO's free educational resources for kids. Thanks for listening.
Thanks for listening. Bye.
Bye.